Okay. In the last class, we introduced the idea of friction for the first time. And here's a quick summary of it. So we looked at our quintessential example of trying to move a trash can. Here it is on the ground. Here is a free body diagram for it. When the trash can is at rest and you're trying to push it, but it's still at rest. Of course, there is the weight, mg down, right? This is the same as the weight of the object, the force of gravity. There is the normal force from the ground pushing upwards. Then you are applying some force F trying to push the trash can to the right, but it has not yet moved. That means it has zero acceleration, it's still at rest, which obviously means that there is a opposing force of friction, which we call the force of static friction because it's still at rest. That must be exactly equal and opposite to the force that you are applying. Because if there's any imbalance between these two forces, there will be a not net force along the x-axis, and then there would be an acceleration and the trash can would move. So what that means is, from our experience, when you try to first push the trash can, it doesn't move, then you'll increase your force, it still doesn't move. And then eventually, once you reach some critical threshold, it starts to move, which means that before it starts to move, this force of static friction is just mimicking exactly what you are doing, right? So here I'm plotting the magnitude of the force of friction versus the force that you are applying. So initially, you apply zero force. That means this F is zero. Then the force of static friction is also zero. The trash can is just sitting there. Then all of a sudden, you increase and you apply some non-zero force F. Then immediately a force of static friction appears of exactly the same magnitude. And as you increase your applied force, the force of static friction also starts to increase in this particular fashion, so that the magnitude of the force of static friction is always exactly equal to the force that you are applying, as long as the trash can is not moving. Any questions on that? Eventually, you keep applying a force. The force of static friction will reach some maximum value here. Again, that's equal to whatever the force you're applying here. And then there's this critical threshold. You apply a force beyond that, and then here the trash can slips all of a sudden, and it starts to move. And then the force of friction starts to also decrease and kind of plateaus as it starts to move. And in that case, you are in this situation over here, where you now have a force of kinetic friction that is opposing the force that you are applying. And from our everyday experience, we know that the force of kinetic friction is a little bit less. It's easier to keep it moving once it's moving. And again, if your applied force is bigger than the force of kinetic friction, then the trash can will accelerate, it'll keep picking up speed. Whereas if you all of a sudden then start to reduce the force you're applying such that it is equal in magnitude to the force of kinetic friction, then the net force in the x direction will be zero, and it will continue to slide with constant velocity. Questions on that? You probably never thought you'd think this deeply about moving a trash can, but the next time that you're doing that, think back to physics 1111. Yes?
So it's true that if that force is zero, acceleration is zero.
If what force is zero, you said?
If the net force.
That's correct. So in fact, that's there was this previous slide here. So if this force is exactly equal and opposite the force of kinetic friction, then in this case, I will say like the F net in the x direction, which is equal to the mass times the acceleration in the x direction, will be zero in that case, and it will move with constant velocity. Okay. So we had started talking about how we can build a model for this force of friction, because it's a complicated thing, right? Again, at a molecular level, it's all the electromagnetic interactions between the atoms in the trash can and the floor. And so we are sort of looking at this at a macroscopic scale, where we're sort of seeing the aggregate effect of all of those molecular interactions. And so we'll build a model for this aggregate net force, force of friction that we see. And here are some experimental observations. One is we notice that the force of friction is proportional to the normal force. Again, if there's something very heavy that's sitting on the floor, the normal force pushing up will also be much greater because something with a large mass will have a big weight, and the normal force has to balance this big weight. And we know that if something has a large weight, then it is harder to get it moving. So therefore, it must mean that the force of friction is related to the normal force. An intuitive way of saying this is if there's something very heavy with a large weight, it's kind of digging into the ground a lot more. And so the ground is pushing up on it with a greater force. And so the molecules and stuff are interacting much more closely, and it's harder for you to push against it. So the force of friction in this way of thinking should be proportional to the normal force. And we also notice that the force of static friction is generally greater than the force of kinetic friction. This is a statement that it's easier to keep it moving once it's moving, but it's harder to get it to move from rest. And of course, this constant of proportionality will involve something called a coefficient of friction, which depends on the chemistry of the surfaces involved. So if you're moving a block of ice on ice, it's easier to move as opposed to moving a trash can on carpet, for example, right? So that coefficient of kinetic, static or kinetic friction depends on the chemistry of the materials. The direction of the frictional force is always opposite the direction of motion. So if you're ever, if something is moving and you want to know what is the direction of the frictional force, it's always opposing the direction of motion. And it turns out from experimental observation that the coefficients of kinetic friction are nearly independent of the area of the contact. It's really about the chemistry of the materials. And so it tends to just scale more with the normal force. So, so here's how we can put all of this together. We say that this is what the magnitude of the static friction looks like. There's this weird inequality here. And why is this inequality here is because remember that as you're trying to get the trash can to move, the force of static friction is just mimicking whatever you are doing. So whatever force you're applying, it's applying that back at you. But then eventually you reach some critical threshold. And at that critical threshold here, I will say that the maximum value of the static friction right before it slips is given by mu s times the normal force. So this mu s here is the coefficient of static friction, which is again depending on the chemistry of the two surfaces involved. And it depends on the normal force, that is how much in contact the two surfaces are. And for the other part where you're not at the maximum, you know, for Fs less than the maximum value, remember that Fs is just equal to the force that you apply. So that is the model we have, that if the normal force is very large, if the coefficient of static friction is very large, then what's going to happen is you're going to have to keep applying a much, much bigger force before you reach the critical threshold before which it starts to move. And then the coefficient of kinetic friction is the friction that force that it experiences once there is relative motion between the surfaces, and that just depends on the normal force times the coefficient of kinetic friction. So here there's not an inequality like the way it was over here. That's just the result right there. And so again, in all these problems, the normal force, if there's something just sitting on a surface, the normal force is just equal to the weight. Right? And so there's that question here. And so now you can see here that there's a table for frictional forces between different types of surfaces. So steel on steel, Coefficient of static friction is 0.74, kinetic friction is 0.57. If I look at something like ice on ice, the coefficient of static friction is much less, 0.1, and the coefficient of kinetic friction is even less, 0.03. Any questions on that? All right, so keep that in mind, and let's go to a top hat question. And I'm going to ask you to calculate the force of kinetic friction in this top hat question. So let's see. All right, so here's the question. You are told that there is a box of mass 10 kilograms. It's sliding across the surface. The coefficient of kinetic friction is 0.5. Calculate the magnitude of the force of kinetic friction. Give your answer in units of newtons. Any questions about the question? So hint here is first calculate what the normal force should be, and then you can use that in the formula for the force of kinetic friction. All right, let me go ahead and start the question. Let me add another 15 seconds, so about 25 seconds left. Let me add another 15. Okay, let's see what we have. Actually forget what the answer is. All right, so most of you got it. It is 49 newtons. 49 newtons. Let me go through that real quick. I guess I can do that here. So again, the idea here is that you have some box or some object of some mass m. It's sliding along the surface, and the force of kinetic friction is equal to mu k times n. So if I were to draw a free body diagram for this box, here's what that looks like. This is the free body diagram for m. Let's say this is our positive x, our positive y. There's the weight acting down, mg. There's the normal force on it acting up from the ground. And then there is the force of kinetic friction, which is opposing the motion, which is this F sub K. Is there any other force acting on this object? Say it again. So does that mean that there is an extra force on it or no? No. And what is that force? So yeah, but I drew that here, right? So that's the force of friction. So there isn't an extra force. So someone may have pushed it to get it going, but once it's moving, then this is the free body diagram. So in fact, it's going to be, is it going to be speeding up or slowing down? Slowing down, right? Because it's moving to the right. It has a net force along the x direction to the left, which means its acceleration is to the left. That means its acceleration and velocity are in opposite directions. It's going to be slowing down as we expect. Eventually it'll come to a rest. But at the moment, this is what the free body diagram looks like. So it does have a non-zero acceleration along the x direction. But for me to use this formula, I need to figure out what is this normal force. And I keep in mind that along the y direction, the net force has to be zero because the object is just sliding along the x direction. So that means the acceleration in the y direction must be zero, which means these two forces must add up to zero. So therefore you get that second law, Newton's second law in y direction tells you that F net in the y direction equaling mass times AY is zero, because the AY is zero. And here the net force is N minus mg, which has to equal zero. Therefore, N is equal to mg. Therefore, N is equal to mg, and therefore, or actually I can just move all of this up. And so now I can write, therefore, that the force of kinetic friction is the coefficient of kinetic friction times mg, just because I can now use this result in here. Now that I know what the normal force is, it's just equal to the weight. And this comes out to be 0.5 times 10 kilograms times 9.80 meters per second squared. And I think this comes out to be 49 newtons. So that is the force of kinetic friction. Any questions on that? Okay. All right. So far we have been looking at problems where we have been kind of working with coordinate systems where the x is kind of horizontal, quote unquote, and the y is vertical. But often you will have problems, and we'll do an example today, where you may have, for example, this object that's sitting on this incline, and then some weird angles and trigonometry sort of come into play. And so we'll go through one example of this on how to deal with that. But the basic philosophy is the same. So for this particular problem, if I were to draw a free body diagram for this object here that's sitting on this ramp, again, the Earth is down here, so it still feels the force of gravity, which is equal to its weight, right? This thing here is equal to mg in magnitude. But notice that the normal force here, the contact force between this ramp and the block, is now normal to this surface, right? Remember, normal force is always perpendicular to the surface. So now the normal force is in this weird direction that is not, it is not back to back from gravity anymore, but it's at some angle. And the force of friction is going to be along the ramp, right? Because this thing is going to try to slide down, and the force of static friction is going to be going in this direction. So the only three forces acting on this object right now are the normal force this way. There's the force of gravity or the weight of the object down, and there's this force of static friction that is preventing it from sliding down at the moment. Questions on that? So you could, do your usual thing where you say that this is your x direction and this is your y direction. Then you can see that your weight is in the negative y direction. But then the problem is that the force of static friction and the normal force, neither of them are aligned with either x or y, but they're at some weird angle. So we now have to find a way to deal with it. Often it turns out that it's simpler in this situation to kind of realign what you're calling your positive x and your positive y. And instead of using this as your coordinate system, you could, but turns out it's more convenient if I align, for example, my x direction down along the incline and a y direction that is perpendicular to the incline. Because then two of the forces are now aligned with either the x or the y axis. And it's only the force of gravity now that's at a weird angle, and we have to kind of deal with that. You could have done it the other way. In that case, gravity is aligned with the y-axis, and the normal and the force of static friction will be at weird angles. But typically, so since there's more forces that are either perpendicular or along the incline, it becomes useful to kind of work with this kind of a coordinate system. Any questions on that? So what this picture here is showing is that because this force of gravity is at a weird angle, what we can do is we can write it as a sum of a component that is along the x-axis plus a component along the y-axis. And so this is the x component of this force of gravity. This is the y component of the force of gravity. Right, and we'll go through it in some detail in a bit. Because then I can forget about this force here because I have resolved it into its components. So now this thing here is this plus this. And now I can look at this force, the force of static friction, the normal force, the component of the gravitational force along the incline, and the component perpendicular to the incline. Those are the four forces that I now work with. And all of them are nicely aligned along the x or along the y. So now I can apply Newton's second law along the x. I can apply Newton's second law along the y, and I'm in business. So the hardest part in some sense is to take this vector here and resolve it into its x and y components. I like that you're actually tilting your head. That's great.
The theta inside the rectangle.
Yes, I'll go through the trigonometry of how we figure out that angle in a bit. Any other questions on this? So yeah, so we're actually going to do an example here. Before I do the example, let me also just quickly mention that there are other types of forces of friction. For example, there can be wind resistance or air resistance. And so in this class, we will mostly be dealing with the force of friction between surfaces. But I think probably in your labs or something, you've looked at wind resistance where the form of the force of the model for the force of friction is a little bit different. It may be proportional to the speed of the object and so forth. Whereas here, between surfaces, we're working with a model where the force of friction is proportional to the normal force. So I'll just kind of mention this, but we won't really do much with it in this course. All right, so here, let's now look at an example problem that kind of puts all these things into play. And let me add a page here. So this is kind of a interesting problem. What it says is, suppose that there is a block of mass 2.5 kilograms resting on a ramp. And if the coefficient of static friction between the block and the ramp is 0.35, what maximum angle can the ramp make with the horizontal before the block starts to slip? So what that means is, let's imagine that there is some surface here, and let's say that there is some block that's sort of sitting here. Everything's good. But then someone says, why don't I put this on a ramp, and maybe I'll start to, I'll put it on a ramp like this. And now the block is sitting on the ramp like this. And now you see that it wants to slide down. Of course, maybe the force of friction here is right now enough for it to not slide down, so it'll kind of just sit there. But then if you were to increase the angle and make it even steeper, then all of a sudden it will start to slide down. So the question that they're asking is, what is this critical angle that you can raise the ramp, and at what critical angle will it start to slip? That is a question that we are being asked. Any questions on that? So let me go ahead and draw the picture here as follows. So let's say that there is this ramp like this. And let's say that I'm now at the critical angle. So let's say that this theta here is the critical angle. So at this point, the block will start to slip. It'll be on the verge of slipping. If you move it just a hair above this theta, it will slip. So here then this is at 90 degrees here, and then this is the mass M. It's sitting there. What is the free body diagram in this case? So let me go ahead and here draw the free body diagram. And let me choose my axes so that my x-axis is in this direction and my y-axis is in this direction. So let me go ahead here and say again, let me draw my x-axis here. Let me draw my y-axis like that. Here is this object, and I'm going to now draw the free body diagram for it. So here is x, here is y. Any questions about what these pictures are representing? So this here is the ramp. This is the ramp right here. And this here is the normal direction to the ramp like that. Well, the first force is the force of gravity. So let me just go ahead and, what color should I use? Maybe I should use, yeah, let's use, so the force of gravity is straight down towards the earth, mg. We're very good with that. The earth is just pulling it down towards the center of the earth. There will be a normal force perpendicular to the ramp. So there is the normal force. And then there is the force of static friction. And in particular, it's on the verge of slipping, right? So we've drawn this at the critical angle. That means if it's on the verge of slipping, it has the maximum force of static friction. And so therefore this Fs, this is Fs max, which will be equal to mu s times n, the coefficient of static friction times the normal force. Any questions on that? Now, I claim that in this picture, so you can see here, first off, in this picture, the normal force, it's good because it's along the y-axis. The force of static friction is along the x-axis. this mg is in some weird angle, so it makes things complicated. I want to just apply Newton's second law along x and along y, but this thing is at a weird angle, so I need to resolve that vector into its x and y components. And I claim that this angle here is what is theta. And let's see if we can figure that out by thinking about it. So here's how you can think about it. So remember that you are imagining that the block was basically on a horizontal surface, and then you increase the angle of the ramp like this. So let's imagine that when it's on the in the horizontal case, let me say for theta equaling 0, for that situation, it looks like this, where m is just sitting here like that, right? That's the theta equaling 0 case, where this angle here is exactly 0. And in that case, your x and your y will be like that, because now the ramp is exactly horizontal. So this x here becomes this, and your vertical is normal to that. So if I were to draw that onto this picture here, it would look something like this, right? This is like your, maybe I'll call this x prime and y prime. This is like your x prime and your y prime. And how do I get from that x prime, y prime to this rotated angle? Well, what I'm starting to do is I'm starting to kind of increase the ramp like this, right? I'm trying to increase its value. And so that means I am trying to take this ramp and I'm moving it up in this direction, which means that this vertical is also moving in this direction, which means that this vertical is also moving in this direction by some angle. Let me take a moment. Right, this thing is also going down. Everything is just rotating like this by some angle. And I'll keep doing this rotation until I reach the angle theta, which basically means that I'll keep rotating this all the way up here until this is theta. And so therefore, that's exactly what I had drawn, which is that this angle here is exactly theta. Any questions on that? And so now that I know that, yeah, go ahead, question.
Why would you not just take the angle from like how you drew the first time, from where like the end of the ramp?
You can take it from anywhere, right? So I could say like, yeah, you could say it like this. This angle here is theta, this angle here is theta, this angle here is theta, and that angle there is theta. So everything is just moved by an angle theta. Does that make sense? And I'm just gonna look at this particular angle here because I'm interested in resolving this vector into its two components. So let me just show you how that works. So now I'm going to, let me just redraw that. So here is your y-axis, your x-axis, this is your x, this is your y, and you now have your normal force this way, your force of static friction, Fs max equals mu Sn, and then you have your force of gravity mg down, and this angle now here is theta, and I'm going to resolve it into something along the negative y direction plus something along the x direction. So I'm writing that mg vector as a sum of two force vectors, something along the negative y plus something along the ramp, the positive x. Right, and then this angle here is 90 degrees. So what that means is that I've now made a right triangle where the hypotenuse here has an angle of mg, sorry, has a magnitude of mg. This side here, by trigonometry, is mg cosine theta, And this side here is mg sine theta. That is how I've resolved those two vectors. Any questions on that? And so let me now clean this up a little bit, because now that I have written this mg as a sum of these two forces, I can just get rid of these forces, this mg force, and just use these two forces instead, since they're all pointing along the x and the y. And so here, let me copy paste here and go to my final way of doing this, where I will just get rid of this mg completely. And what I'll do next is I will take this mg sine theta and I'm going to move it up here, exactly along the ramp. Any questions on that? So this is now the free body diagram on the object where all the forces acting on it have been resolved into components along the x and the y axes. So if there was any angle of force that was pointing at a weird angle, we just resolve it into its components. And now we're good to go, because now I can apply Newton's second law along the x and Newton's second law along the y. And the thing that we are trying to solve for is the critical angle theta. So we are trying to solve for critical angle theta such that the object is on the verge of slipping, but still stationary. So the verge of slipping that phrase means that I can say that Fs max is mu s let me say it this way. Fs max is equal to mu s times n. So when I say that it's on the verge of slipping, that's what that means, right? That the force of static friction has reached its maximum value. But it is still stationary. That's English for saying that ax is 0 and ay is 0. It has no acceleration. Yes.
Can you just remind me how you know that we can move that mg sine theta to the other?
Like how I moved it from here to here? Because remember, I can always slide vectors parallel to themselves as long as I don't change their orientation or magnitude. Right, because a vector is pointing in some direction with some magnitude, it's just saying take so many steps in that direction. So whether it's over here or whether it's over here, it doesn't matter. Both of them are telling you take so many steps from wherever you are, take so many steps along in a direction that is parallel to the x-axis. So it's containing the same information. So remember, like when we did in the early on, we were trying to add vectors, we would slide them around, move them tip to tail. So that's the same thing that I'm doing here. All right. Let's go here, let's add a page. All right, so I just kind of went deliberately slow through this. Once you get the hang of it, you can probably draw this pretty quickly, but I just want the first time I'm going through it a little bit slowly. So let's see how we can now solve for x. Solve for theta. Let me now do Newton's second law. Right, again, the philosophy in all these problems is you draw the free body diagram and then you apply Newton's second law write down the equations from Newton's second law, and solve for the variable of interest. So let me say here along the x direction, what do I get? I get mg sine theta minus mu sn has to equal 0 because the acceleration, the net force is 0 for 0 acceleration. To be a bit more explicit here, let me say that F net x is equal to mass times acceleration in the x direction, which is 0. So that's Newton's second law there. And then I can do the same in the y direction. Here again, I will have F net y equals may, which is 0, because the object is at rest. And again, I just look at, and by the way, how did I arrive at this equation here? I'm just reading my free body diagram, right? I have mg sine theta in the positive x minus mu sn in the negative x. So therefore, I have that. They have to add up to 0. And similarly here, I have plus n minus mg cosine theta. So I end up here with n minus mg cosine theta. That is equal to 0. So notice that this is like equation 1. This is like equation 2. We have two unknowns. Which are n and theta. We don't know the normal force yet, and we don't know the critical angle. The critical angle is what we're interested in. But we have two equations, so we can solve for them simultaneously. Any questions on that? So we see here from 2, we get that n is equal to mg cosine theta. Notice that the normal force is not equal to the weight mg, as it is in the case of a horizontal thing, but this normal force only has to balance this component of the force of gravity, not the entire force of gravity, because some of the force of gravity is along the incline. And you may notice this when you stand on an incline, you don't feel as stable as when you do it when you're on a horizontal ground. The horizontal ground is pushing up on you, you feel much more firmer, whereas when you're standing on a slide, you don't feel like the ground is pushing up on you as much, and you have this tendency to slide. And so I can now use this in 1 to get at the thing that I'm interested in. So I get here mg sine theta minus mu s times the normal force, which is mg cosine theta, which has to equal 0. And therefore, I can divide out the mg on both sides. And therefore, I end up with, mu s is just equal to sine of theta divided by cosine of theta, which is equal to, what is that we're solving for? We're solving for theta. So therefore, this is equal to tangent of theta. And so therefore, I can now go ahead and say that theta is equal to the tangent inverse of the coefficient of static friction. And this was given to us as tangent inverse of, what was it? 0.350. And if I look at the numbers, that comes out to theta as 19.3 degrees. That is the critical angle at which the object will start to slip. Any questions on that? All right, I think I'm out of time, so let me go ahead and stop there.